Hello everyone, today I will present our paper accepted by CVPR 26, Personalized Image Description from Attention Sequences. Personalized image description is to describe an image in the style of who is describing that. For these different individuals, for example in the figure shown, the subject 1 and 2, even if they are viewing the same image, their description will be very different. Not only the length, but also the objects that are mentioned, in what detail, and in what order. The limitation of existing approaches on personalized image description tasks is they mainly focus on language styles such as phrase, tones, and overlook a very important factor, human attention. So what is human attention? It is the sequence of fixations that an individual makes when looking at an image. Take the figure as an example. Each circle is a fixation point that the human is viewing at. The size of the circle indicating the duration that the human is viewing this point, and the numbers indicating the order of those fixations. So from the figure, we could see that for different subjects viewing in the same image, they will have really different fixation patterns. Why human attention is important for personalized image description task is the human attention determines how an individual will describe the image. For example, the important information like where they will look at, in what order, and for how long will shape how they describe the image, as shown in the example in the figure. To solve this problem, we propose the human attention-guided personalized image description model. Here, we introduce Deeper. It is a model to learn the user representation, which is aware of the multimodal intro and inter-user information. In Deeper, we also introduce the trajectory decoder as an auxiliary module to reconstruct the attention sequence, encourage the user representation to retain key attention dynamics. Our model is also able to quickly adapt to the new users with a few support samples without any further fine-tuning. Now let's go to the method. Here, we first have the input image, attention sequence, and image descriptions. We will input them to Deeper. Then Deeper will give us a subject embedding. Then we will use this subject embedding to constrain the multimodal large language model to generate the personalized image description. First, how we encode the attention sequence into Deeper is we will change the fixations into bounding boxes because they are larger and have more information. Our model is able to deal with different types of fixations with or without the words grounding. Then, for each bounding box, we will compute the overlap between the box and the image tokens, and we average them to get the box features. Now let's go to Deeper. First, Deeper will take the image, trajectory, and text features into the dual context encoder. The purpose of the dual context encoder is to exchange the information between the trajectory and the text. After that, we will get the dual context features. Then, the subject embedding extractor will initialize a subject query and attend to the dual context features to get the subject embedding. The subject embedding will capture the consistent perceptual linguistic behavior across different images. We also have an auxiliary module, the trajectory decoder, that will take the subject embedding and other context features to reconstruct the trajectory. It will help to enforce the integration of personalized viewing behaviors into dual context features and subject embedding. We have two training stages. In stage 1, we only train Deeper with contrastive learning plus the subject ID classification. For different descriptions from the same subject, we hope the subject embedding derived from them will be put together. But for descriptions from different subjects, we hope that the contrastive learning will push them apart. This operation will help to build a discriminative subject embedding space to support the few-shot adaptation to unseen subjects. We also have an auxiliary loss to reconstruct the input sequence of bounding boxes by compute the L1 loss of the bounding box coordinates. In stage 2, we use the supervised fine-tuning to optimize the subject embedding extractor from the image description task. And we'll also keep the contrastive loss to make sure that our model can keep the learned user embedding space. We test our model on 4 different datasets and the 3 tasks of human attention collection. A notable thing compared with the prompt tuning one, which is a common method for personalized multimodal large language model, is the significant improvement of our method indicates that deeper can help with extracting a robust and consistent subject embedding that encodes the perceptual and linguistic style. Then we go to the few-shot setting on unseen subjects. Notably, our method doesn't require any further fine-tuning. We directly infer the subject embedding from deeper by the support samples, and we run the inference for the unseen user conditional text generation. And for unseen subject on different datasets, we all achieve the best performance. Here are some qualitative results of both seen and unseen unlocalized narratives, and we have more visualizations in the main paper and the supplementary. An interesting thing is the subject embedding space because we have implemented the contrastive learning. So we could see that from both the seen and unseen subject space, the subject embedding from the same subject but different images are clustered together, and from the different subjects are separated apart. That means the deeper itself can learn a robust subject embedding space, which can benefit the unseen users because the unseen users can directly infer the information from its pre-trained seen subjects. For more details, please check our paper and supplementary. And this project is supported by the US NSF grant. Thank you for listening.